Next, we're going to talk about how the basic holomorphic closure properties will give us a bunch of formula for power series. So the first thing to point out is that since we know analytic and holomorphic are the same, if I have two analytic functions on the same domain, then their product is analytic, no big deal. But how do we compute the power series? So we'll do this all just at 0 for convenience, but you could always move this to a different point and have power series centered at something like z0. But the power series product is computed as if you were going to distribute these infinite sums. So the power series you get is the convolution product. So if I have a power series built out of ANs and a power series built out of BMs, then the CK coefficient of the product power series, which I know to be analytic by the above, is given by this formula. So I'll sum from n equals 0 to k of an times b k minus n, or you can switch the order in the formula and get the same thing. And certainly the radius of convergence has to be at least the radius of convergence of the minimum of the radii of convergence of the two power series. And we'll see in a moment that we get this formula straight from algebraic facts. It's not an issue of convergence, but then we do get out of this that this convolution product will have to converge where we say it does. But we'll get it without actually doing any analysis. So here's just a basic example. If I have 1 over 1 minus z, which has the simplest power series possible, and principal log of 1 over 1 minus z, it has this power series, z to the m over m. Then if you multiply these two, you do this convolution product. But what you end up doing is adding up the first k terms in the harmonic series, so you get these hk's, 1 plus a half all the way up to 1 over k. Now, how do you show that you get this convolution product? Well, you could do it analytically, but it's straightforward to show it algebraically. So if I take f and I write out the first, the terms going up to z to the capital N, its power series, then f minus fn will start at z to the n plus 1, and by our local description of analytic functions, I can factor that out and have this analytic. And so this thing here, this whole thing, well, it's only going to have power series terms starting at z to the n plus 1. And I'll do the same thing with g. I'll break it up into gn, and then g minus gn times this leftover term. And now if this is f and if this is g and I multiply them, well, I'll get fn, gn. And then when you distribute these terms, so I would really have fn plus z to the n plus 1 fn tilde times gn plus z to the n plus 1 gn tilde. When you distribute this product, well, the next thing that happens is you'll get z to the n plus 1 times analytic stuff. So in this product, let's call this h, I'll get fn gn plus z to the n plus 1 times analytic stuff. So this part is not going to contribute to the nth coefficient of h, or the cn coefficient. But the part that will contribute is this product of the first, of the beginnings of the power series of f and g. And so these are two polynomials, and you can just compute it straight from algebra that the coefficient of z to the n in this product is going to be what you get by matching the 0 term of f with the nth term of g, the first coefficient, the z to the 1 coefficient of f with the z to the n minus 1 coefficient of g all the way down the line, so that you get this convolution product. We can do the same thing with division. It just gets a little more complicated. So if I have f and g analytic, then f divided by g is analytic whenever g is non-zero. So I can do this with power series. And if I have b0 non-zero in this bottom power series, then it's non-vanishing near zero. So I can do this, and I know by the theory that I'll get an analytic function. And since I know I'll get an analytic function, it makes it easier to sort of solve for the coefficients. So these coefficients, dk, are computable through a triangular linear system. You basically solve for them by writing f over g equals h, and then you solve for h by doing the multiplication, f equals gh. And you get that the kth coefficient will only depend on the 0 through k coefficients of f and g. So here's just a simple example. Let's let f be this function z over e to the z minus 1. Now here the top and bottom do vanish, but I can realize this as 1 over a non-vanishing analytic function, because e to the z minus 1 divided by z, I can just write out its power series. Right here, it's just a shifted version of the power series of e to the z with the plus 1 missing. And 1 over this has to be equal to a power series because this is non-vanishing at 0. And so what do? I take the power series that I know, which is in the bottom, times the one I'm trying to figure out, and that has to equal the power series of just 1. So you can match the 0 terms, so 1 times d0 will give me the first term here, which is 1. So you get d0 has to be 1, and you keep going through this. So I look at the coefficient of z has to be 0. So 1 times d1 plus 1/2 times d0 has to be 0, and then you can just solve that d1 has to be negative 1/2, and you can keep doing this and get a bunch of other coefficients. d2 is 1/12, d3 is 0, d4 is negative 1 over 720. And so we get the first few coefficients of this function here, z over e to the z minus 1. I'm just going to point out here that if you normalize it so that you write them as bn over n factorial, these numbers have a special name. They're called the Bernoulli numbers. We'll come back to them at some point in the course. But the explanation for why you can do this is just very similar for what we wrote out for products. So you write out f and g in terms of their starting polynomials, and then you look at this division, and it's equal to an analytic function, which we break up in the same way. But then when you multiply this denominator over to here, well, you'll get that fn plus this term equals gnhn plus this higher order analytic stuff. And so this will not influence the lower order stuff on the other side. So the coefficient of f, an, is going to be equal to this convolution product of the beginning terms of g and h. And if I already know d0 through dn minus 1, and I know that b0 is non-zero, well, I can solve for dn in this. So I guess I would get 1 over b0 an minus all of these terms here. And so this is how it's a triangular system. So if I solve it iteratively, I can always get the nth term knowing the previous terms and the previous coefficients. Next, let's take a look at composition. So as we already know, if we have an analytic function on U and an analytic function G that maps from V to U, then the composition is analytic. So what does this say about power series? Well, if you sort of normalize things so that G maps 0 to 0 and F is a power series centered at 0, then we can figure out the coefficients of the composition, which has to be analytic. So just by definition, plugging G into the power series of F gives you this infinite sum, but this has to equal a straightforward power series. So the coefficients Cn, we can compute them, and they only depend on the earlier coefficients of F and G. Let's do it with an example first and then see how it works generally. So the exponential of z over 1 minus z, I can do this by plugging it right into the power series. And here are the initial terms, 1 plus z over 1 minus z, 1 half, z squared over 1 minus z squared, and so on. And basically the point is, since this vanishes at 0, it has a factor of z, so these later terms will all start at a higher order. So this starts at order 2, the next one will start at order 3, so it doesn't influence the earlier stuff that happens. So I can get out of this that the first coefficient has to be 1 because these later terms won't influence it. Then to find the coefficient of z, well, I know that I have a factor of z here, and I can figure out the coefficient of z in this power series because this is just a piece of the geometric series. Then I know that this doesn't influence it at all. But the z squared term is a little more complicated, so I do have a z squared term here, and then I have a z squared term in this power series, which just comes from the constant term, so I'll get 1 plus 1 half z squared, and then you can go through this even further to compute the coefficient of z cubed. Very briefly, we can justify how this works. So we'll write out F and G as we have been, using just the beginning sections of their power series. So if I plug G into F, then I'll have Fn with G plugged into it, and then I'll have that, I'll have another term that's obtained by putting G into the term Zn plus 1 Fn tilde of Z. So I'll just be putting G into that. But I know all of this is analytic, and I know that G vanishes to at least order 1, so then this has to vanish to order n plus 1 times this analytic thing. So this part doesn't influence my computation of the nth coefficient of this power series. Also, when I plug G into this first part, I only have to worry about Gn because I've also written G in this form, and when I plug this into Fn, well, the parts involving anytime I hit, anytime I use this term in there, it's going to give me something with a power of z to the power n plus 1 or higher. So I only need to compute the composition of fn with gn, and this is just a composition of polynomials, which is just an algebraic operation. So to compute the nth coefficient of the composition is just a straightforward algebraic thing. And although we know it is analytic and therefore has to have certain convergent properties, this just shows us that it's just an algebraic operation.